Hello HMS modelers, I'm Emily Moe with the U.S. Army Corps of Engineers St. Paul District. In this video, I'll provide a brief introduction to snowmelt modeling within HEC-HMS. In some regions, snow represents a substantial volume of water storage within the watershed that can produce powerful impacts as it melts, contributing significant additional inflow into rivers, streams, and reservoirs. A large portion of the United States is impacted by the effects of snowmelt. Within the U.S. Army Corps of Engineers, the effects of snowmelt can impact reservoir operations, produce flooding, and impact planning and design studies. The goal of snow hydrology is to track the volume of water within the watershed by estimating snow accumulation and ablation in terms of SWE, snow water equivalent. Tracking the volume of SWE within a watershed allows us to estimate the peak timing and magnitude of melt events that can then be routed through the watershed to assess possible impacts. HMS utilizes the temperature index method to simulate snowmelt processes. The temperature index method essentially looks at falling precipitation with respect to air temperature in order to determine whether that precipitation is falling as rain or as snow. If the temperature is over a specified limit, it's considered rain and falls as liquid water. If the temperature is under the set threshold, the precipitation volume is added to the snowpack. Next, the temperature index method determines if the air temperature is above freezing. If it's below freezing, no change in the snowpack occurs. If it's above freezing, the snowpack begins to melt and is added to the liquid water volume within the snowpack. Next, HMS considers, is the snowpack temperature below freezing? If yes, the liquid water within the snowpack refreezes. If the temperature of the snowpack is above freezing, the amount of liquid water within the snowpack is considered. If that liquid water volume within the snowpack exceeds a specified percentage of the overall snowpack, that liquid water limit is exceeded and water is then released from the snowpack. Additional melt may occur due to ground melt, and the melted snowpack is then released as liquid water to the soil's surface as runoff. The flowchart for the temperature index method model shows how the information on the following slides come together as a simulation algorithm. In HMS version 4.7, the snowmelt component is activated within the meteorologic model settings. There are two approaches to snowmelt modeling within HMS. The first is the general temperature index method, which involves a lumped parameter approach, which assumes that snow parameters and melt is homogeneous within each subbasin. This method may be most appropriate when temperatures are consistent throughout each subbasin, or if snowmelt occurs fairly consistently throughout the entire subbasin. The second method is the gridded temperature index method, which involves gridded input parameters. The gridded approach allows for increased variability of key data within each subbasin, such as temperature distribution, initial snowpack conditions, and melt rates throughout each subbasin. Both methods share many of the same data requirements, with the key differences being the gridded temperature index method requires gridded temperature data versus point source temperature gauge data. The gridded method requires additional initial condition grids for key parameters such as snow water equivalent, cold content, and more. The temperature index method can apply a lapse rate, which is useful for subbasins with significant elevation variation. Let's take a closer look at the temperature index method. The parameters required for this method must be assigned by subbasin within the meteorologic model. The figure in the center of this slide shows the temperature index dialog. The far right of this slide includes common parameter values as well as which parameters are typically adjusted during calibration. The melt rate is by far the most sensitive parameter that will always have a direct impact on the snow calibration. Now let's take a look at the gridded temperature index method. Once again, the parameters for this method must be assigned by subbasin within the meteorologic model. The figure in the center of this slide shows the gridded temperature index dialog. Initial values for the gridded temperature index method can be set to spatially distributed parameter grids as shown here, or they can be set to default values, which then reverts initial conditions similarly to the general temperature index method, but it still determines future snowmelt on a gridded distribution. The far right of the page includes common parameter values as well as which parameters are typically adjusted during calibration. Observed data is desirable for initial snow water equivalent, SWE, and cold content, but zero value grids can be used for the remaining gridded initial conditions if no observed initial data is available. Once again, the melt rate is by far the most sensitive parameter in the gridded temperature index approach. Just like in the temperature index approach, it will always have a direct impact on the snow calibration. When modeling snowmelt within HMS, you must first calibrate the melting of the snow component. To do this, we consider the snow water equivalent, the SWE, within the model and calibrate the modeled SWE to closely mirror the actual observed SWE. Once the snowpack is melting similarly to the observed data, you can proceed with the runoff calibration to complete the event. So where can you find observed snow data? Luckily, there are several snow observation sites available throughout the western United States, shown here on the map in blue. These western sources include both snow telemetry or SNOTEL sites, which are automated data collection sites, as well as snow course sites where data is manually collected. Unfortunately, observed snow data is more difficult to come by in the Midwest and Eastern United States, with just a handful of SCAN or Soil Climate Analysis Network sites, shown here in red, available in these areas. In regions where observed snow data is scarce, an alternate source may be adopted as observed snow data, the Snow Data Assimilation System, or SNODAS. SNODAS is actually a snow simulation model produced by the National Operational Hydrologic Remote Sensing Center, NORISC. Benefits of the SNODAS data is that it's available nationwide and includes information required for the HMS temperature index and gridded temperature index snowmelt methods. While the SNODAS data is actually model output, the SNODAS model is corrected with observed data from gamma flights and point observations. Any model corrections then get documented online. Drawbacks of using the SNODAS data is that it is in itself model output and not actually observed data. Updates made to the SNODAS model from field observations are not always timely, and there's still a large discrepancy of observed data availability between the Western and the non-Western United States. Let's wrap up with some key takeaways. First and foremost, snowmelt is an important hydrologic driver throughout many watersheds. The snowmelt component within HMS should be calibrated first before the typical runoff calibration is started. Several additional parameters are required to model snowmelt within HMS, including temperature, snow water equivalent, and melt rates. However, observed or estimated observed data is available for most watersheds within the U.S.